It's great to be here, and it's great to have so many partners. We're also in the breakthrough energy portfolio, and so it's fun to see learn a bit more about our peers in that space. I'm Ben Serrurier. I lead the government affairs and policy team at Fervo Energy. We are an enhanced geothermal energy startup and developer. I mean, that startup term is probably a bit wishy-washy. We're 7 years old now and building a large project, and I think that goes beyond startup at this point. But I want to talk a little bit about the role of geothermal on the grid. It's not something that has been a super hot topic maybe over the last 20 years, but is having a little bit of a moment. And can talk a little bit about why that is and why we think that's going to continue over the next few years. So speaking first about the importance of clean firm capacity, don't need to belabor the point since it's certainly a theme today. But I wanted to call out that geothermal is often overlooked in this category. It's one of the few technologies that, at least in the Department of Energy, is telling checks all the boxes when we're talking about adding new clean firm technology to the grid. And so when you look at a chart like this, it's pretty easy to say, wait a second, why do we only have 4 to 5 gigawatts of geothermal on the grid today? And why is it only providing 0.4% of our country's energy needs? 0.4%. It's not a lot. And the reason is that conventional geothermal, the technology that's been deployed today and is a mature technology, is very effective where it works, but it's highly constrained. What you basically do, and I talk a lot about how geothermal is not particularly complicated, but it is pretty complex. The concept's pretty straightforward. It's hot under the earth. You drill into that heat and you circulate water to extract that heat and use that water to drive a turbine on the surface to generate electricity. In conventional geothermal, that approach relies on very specific subsurface conditions that have naturally occurring permeability. You need to have sufficiently high heat that you can extract and drive a turbine, so it needs to be economically high enough heat. You need to be able to drill to it, so it can't be way too deep under the earth. The rock itself needs to be permeable, so you can circulate water that can be extracted, so you can get the heat out. And there's actually sort of a sneaky fifth thing here, which is that you need to know that it's there, which isn't always as easy when these conditions are existing under the subsurface. And so we often see geothermal projects in places like the geysers or Iceland or in Utah, more specifically Sulphurdale, places where there are surface expressions of that subsurface condition. The constraints on these resources have meant that projects tend to be small, they tend to be expensive, they're bespoke in their drilling approaches, and there's not a lot of resource. And frankly, sometimes that resource has turned out not to be what we expected, and so there's been underperformance of projects. All of these conditions are not uniformly constrained across the US and around the world. In particular, I want to call out permeability as one of the key metrics of success of a geothermal project that is particularly constrained. But we can overcome that using next generation geothermal technology. So Fervo's approach to EGS is built off of the success of the oil and gas industry and the same technologies that unlocked the shale boom for the last 20 odd years. Predominantly horizontal drilling, reservoir engineering, stimulation techniques, and distributed fiber optics, so subsurface data collection and observation technologies. What we do is we drill down, say, 8,000 to 12,000 feet. We drill horizontally another 3,000 to 5,000 feet. We inject into a hot piece of granite, basically impermeable rock that's 400, 425 degrees Fahrenheit. We inject high pressure water and sand. That water and sand creates fractures, hundreds of fractures across that rock, depending on how many stages we stimulate. And then we connect those fractures with another horizontal well, opening up a large piece of hot granite that now looks a lot like a naturally occurring conventional geothermal reservoir. However, we've engineered this one. So we have a high degree of confidence in the flow through that reservoir, the geologic conditions, and the ability to replicate that drilling technique and the stimulation approach across a large basin. That allows us to basically have a modular approach to geothermal technology development. What this does is that it opens up, and I'm sorry for all the text on this slide. It's better if you take it home and read it. But it opens up massive new resources across the West and across the US, predominantly in the West because we have the best geothermal resource here in the West, but that certainly isn't the limitation to the growth of this technology. We're talking thousands and thousands of gigawatts of technical potential. And perhaps more importantly, when you think about the shale revolution, it wasn't just that shale unlocked hydrocarbon resources that were previously uneconomic, but it opened up a style of development that enabled a rapid increase in drilling productivity and better financing opportunities. So instead of having a really bespoke long development process like you have in conventional geothermal, the wells we drill, we don't necessarily need to do resource confirmation wells. The wells we drill starting from day one are the ones that we use in our injection and production of our actual facility. We have a high degree of confidence in our subsurface modeling, and then we can copy and paste those well design across a whole basin. That allows us to unlock multiple phases of projects, which I'll talk about in a moment when I talk about our project development. So this is all well and good on paper, but it's important to think about, does it actually work in practice? Enhanced geothermal has been tried by the US government since the 70s. There was a research project in New Mexico called Fenton Hill, and it kind of worked. Like they had some connectivity, but they didn't really get quite enough water back through the subsurface to drive a turbine economically. It's really been the enhancements in oil and gas technology and now applied to geothermal that have really unlocked the economic potential of this technology. And we saw that with our first pilot project called Project Red in Northern Nevada. This was a great idea, and it wasn't until we were able to partner with Google to actually bring it to fruition, where we drilled 2 horizontal wells, which you see designed here on the right, next to a geothermal project, a conventional project that was underperforming. And the project that was underperforming tried to expand their well field, and they said, what if we went a little bit outside of the area where it's the sweet spot, basically? And they got into geology that was quickly uneconomic because there wasn't enough permeability in that rock. We drilled 2 horizontal wells, the first 2 horizontal wells ever drilled in geothermal, stimulated the reservoir, and circulated water between those 2 wells, putting that steam directly into the power plant, generating electricity and increasing that production. These are now the 2 most productive wells at this conventional geothermal site in Northern Nevada. This demonstrated that the technology works, and the next step was to scale it up. I should note these well production was about 3.5 megawatts at this pilot project. This data is now frankly a little stale because we've got 10 months of operating data. But what this demonstrates, without getting too much into the fine print here, is that our actual production remained quite stable. Some of the concerns around enhanced geothermal have to do with whether you're actually connecting all of your fractures in the subsurface. Do you have a naturally occurring fracture that's stealing your injection fluid and kind of taking it in the wrong direction, doesn't get returned to the surface for generation? Any of those challenges can decrease production and mean that you have an uneconomic project. But because of the fiber optic sensing and because of the increases in production, technology around well stimulation, we have a really clear idea of what's happening in the subsurface, and that it allows us to circulate all the water that we pump down, we pump back up. This success at Project Red gave us the green light to go ahead and start developing our first greenfield project, which is here in Utah. It's called the Cape Station Project. It's in Beaver County, outside the town of Milford. It's a 400 megawatt project that's coming online in 2 phases. First phase, COD, is 2026. It's 90 megawatt net generation on the first phase. Second phase is 238 megawatts, comes online in 2028. This project is fully contracted to serve load-serving entities in California who have particularly keen near-term need for firm capacity. But I should note that it's the first 2 phases of what could be 2 to 5 gigawatt resource potential there in that valley, depending on sort of P10, P90. We have a very high degree of confidence, especially now that we've been drilling in the subsurface and have a well-characterized resource there, that we could continue developing this out like a basin development, as you see in places like the Permian, where we have a sweet spot. We can make a particularly large resource from it rather quickly because of the learning curves that we get from drilling. And that's what I want to talk about here before pulling it back to talk about bringing on new projects to meet the load that's being proposed across the West. Drilling is a huge expense, right? You think about a gas plant, you can build a gas generator and you don't have to worry about drilling for natural gas, right? You just plug into the pipeline, someone else's problem to deal with the fuel. For geothermal, we have to build the fuel source, then we have to build the power plant. So drilling can be up to 50% or more of the CapEx for a project. And it's certainly where a lot of the risk has been held in these projects historically. What we've shown at Google, or shown at Fervo, now that we have 14 horizontal wells drilled at Project Cape, is that we're seeing significant learning curves in how fast we can build these wells. The rate of progress for our first well in Utah was about 65 feet per day. Per hour. We have increased that rate of progress in our final well. I'm taking these off of memory because our data is just released on Tuesday, is down to about 35. Sorry, it started 35, now it's at 65. This is why I shouldn't have led with this. So we've increased that by basically a factor of 2, and we've gotten our drill times from spud to total depth, spud being when your drill bit hits the dirt. First, around 70 days to get wells drilled is now under 20. We see how that compares to conventional drilling in the gray lines. These are the wells that were drilled at that conventional site in northern Nevada. The red lines here, Project Red, our very first horizontal wells ever. And then finally, you see some of the wells that we're drilling today at Project Cape. That significant increase in speed allows us to build the project faster, bring it online faster, and go for bigger scale as it matches with the load growth that we're seeing on a near-term basis. It also means we have much more economic projects. The first wells are the most expensive wells. They take the longest amount of time. We don't know what we're drilling into exactly yet until you actually do it. And so what you can see here is we've converted those time per well basically into a cost per foot metric. And we've brought the cost of our drilling down significantly. What is not particularly well shown here is that wells 6, 7, and 8 there at Cape went deeper, used a different design so they had larger production and had a larger well bore, which increases larger production. And so over time, we're increasing the energy density of these wells. Our flow test at Project Cape produced 10 megawatts, which is 3 times what we produced out of our pilot project. And we have a pathway of development in our next phase that we anticipate 16 megawatts per production well. Fervo's got about 16 gigawatts of potential on a P50 basis across the West. And so you can start to think about what this profile of development could look like, starting, say, in Nevada, where we have a contract to bring on 115 megawatts in a first phase with Google in 2030. But that's a potentially multi-gigawatt resource at that same site. And so as we commercialize on the first phase, we can quite rapidly scale that up with a 24/7 firm solution that's increasingly economic as we bring down these capital costs. Look forward to talking about this.